All right, let's dive right in.
Yeah.
We all know what a ship is. We see them all the time. But what exactly is a ship made of?
Yeah, and I guess
And how do we even start to measure its size and all the things it can do?
yeah.
You might think, oh, it's just how long it is, how heavy it is. But there's a whole world of detail beneath the surface, literally.
Oh, yes.
Today, we are going deep into the building blocks of ships and all the ways we classify them, all based on a collection of really amazing learning materials that you shared.
Right.
So our mission is to unpack, like, everything.
Yeah.
Like the types of steel they use to build these things, to the systems that help them, navigate the oceans and stay safe. Your sources cover a lot, from the very definition of tonnage, what does that even mean?
Right.
To the physics of how a rudder works,
Yeah.
all the way to the critical safety regulations that every ship has to follow. We'll be pulling out the most intriguing details to give you, well, hopefully, a really thorough understanding. So get ready for some surprising facts, some clear explanations, and hopefully a few aha moments as we go through this detailed landscape of shipbuilding and naval architecture.
All right. Sounds good. It really is remarkable how much there is to consider when you start to look closely at ships and how they're built and designed.
Yeah.
Maybe we should just start with something seemingly straightforward, but it gets pretty complex. Tonnage.
Yeah.
You hear that word, you probably think, okay, how much does a ship weigh?
Right, like how much it weighs or how much it can carry, that kind of thing.
Yeah, and that's what most people think, but it's not actually weight. And the history is kind of interesting. The word ton used to refer to like those big barrels, those casks they used to carry wine on ships.
Oh, wow.
And from that, they developed the term tonnage, which was really a measure of the volume of those casks.
Okay.
So it was a way to, in a way, it indicated the ship's carrying capacity, but in terms of these wine containers.
So they were paying like port fees based on like how much wine they could carry.
Exactly.
That's pretty wild. I had no idea. It's funny to think that something so technical as ship classification, started with barrels of wine.
Yeah. Well, it was a way to kind of figure out the size and therefore, how much money a ship could potentially make.
Yeah.
And that naturally kind of led to it being used for taxation and port dues.
Oh, okay.
And this historical connection to volume is key to understanding, what tonnage actually means today.
Okay, so if it's not weight, what is this gross tonnage, this GT that we always hear about?
Right. So gross tonnage is a measure of the total enclosed volume of a ship.
Okay.
And it's registered, with the IMO, the International Maritime Organization, and also classification societies like Lloyd's Register of Shipping. We've all heard of Lloyd's. But just to be really clear, it's not the volume of the ship itself. It's not the carrying capacity. It's kind of this more abstract number that actually forms the basis for a whole lot of things, from the port fees you might have to pay to the safety regulations that the ship has to adhere to.
So it's not about like how much stuff it's carrying. It's really about the volume of the enclosed spaces within the ship itself.
Precisely. Yeah.
That's really interesting. So how does a ship actually get this number? Like, what is the process?
Right. So when a ship's getting close to being finished, the shipyard, acting on behalf of the owner, of course,
Yeah.
applies for registration. And they give a whole bunch of details about the vessel, like the main particulars, things like its length and its breadth and its depth, as well as, where it's going to be registered and like what classification society it's built to.
Okay, and then who assigns the GT in the registration?
Well, it gets registered with an organization like IHS Fairplay, which is like a maritime information service.
Yeah.
And they often act on behalf of the IMO. And once it's registered with the IMO, it gets its own unique IMO number. This is really important.
Okay.
This number stays with the ship for its entire life, even if it changes owners or even if it changes the country it's registered in. That IMO number is always the same.
That makes sense, like for tracking and safety purposes, I imagine.
Yeah.
Now, you mentioned in the outline something called the International Tonnage Convention. What's that?
Well, this is a convention that was established by the IMO back in 1969.
Okay.
And the point was to create a system for measuring tonnage that everyone could agree on.
Uh-huh.
Because before that, different countries had their own rules, which could get pretty messy.
Yeah, I can see that.
And so this convention finally came into force on July 18th, 1982.
Okay.
And that meant any ship built after that date had to be measured this way.
And what about all the ships that were already built?
Yeah. So for the older ships, they had a bit of a grace period,
Okay.
They could choose to stick with their existing tonnage measurements for up to 12 years, but by 1994, everyone had to comply.
Gotcha.
This ensured that there was a standardized global system, which is really important.
Absolutely. So can we get a sense of scale? Like, how big are these GT numbers we're talking about? You had some pretty big ships listed in the outline.
Oh, yeah. So, for example, the Oasis of the Seas, that massive cruise ship,
Uh-huh.
has a gross tonnage of 225,282.
Wow.
And there's this global class ship, which is being built for Star Cruises.
Okay.
It was supposed to be delivered around 2020, but, things happen.
Right.
It has a projected GT of over 200,000. That would make it one of the largest passenger ships ever built, at least in Germany where it's being built, and probably worldwide.
That's huge.
Okay.
So who actually does the measuring in the certification?
Well, that responsibility lies with the maritime authority of the country where the ship is registered.
Makes sense.
But most countries actually authorize classification societies, organizations like the Indian Register of Shipping,
Right.
to do it for them. These societies have the experts, and they're all over the world, so it's a lot easier for them to do the measuring and issue the official certificates.
Yeah, I bet that really streamlines things.
It does. It does.
So when they're measuring for gross tonnage, do they, like, measure every nook and cranny? Do they count the space inside the walls, the insulation, that kind of thing?
That's a good question. Actually, any insulation or linings inside the hull, they don't count those when they're calculating the tonnage.
Okay.
So they use what are called the molded dimensions, basically, the measurements of the actual structure itself.
Gotcha.
And nowadays, with all the fancy software, designers and surveyors can calculate these tonnages right in the drawing office using the ship's lines plan. It's pretty sophisticated.
Wow, that is really interesting. So we've learned how it's measured and what it represents.
Yeah.
Why is gross tonnage really significant? Like, why do we even care about this number?
Well, there are several reasons. First of all, as we mentioned, it's a pure number that's directly related to the volume. There are no units, it's just a number.
Right.
And the IMO number that's assigned during registration that's permanently marked on the hull and in the engine room. So that unique identifier stays with the ship forever.
That has to be good for tracking. And safety, probably, too.
Precisely.
Oh.
But even more importantly, a lot of port fees for using docks, dry docks, moorings, that kind of thing, are often based on the gross tonnage.
So the bigger you are, the more you pay.
Exactly. But it goes beyond just costs. It also dictates a lot of the international safety rules and regulations that apply to a ship, like MARPOL for preventing pollution.
Yeah.
SOLAS, which is all about safety of life at sea, things like lifeboats and firefighting equipment.
Right.
And COLREG, which is the collision regulations, how ships are supposed to avoid each other. These all depend on the tonnage.
So a bigger ship, by tonnage, might have more stringent safety requirements because it poses a greater potential risk. Is that what you're saying?
Yes, exactly. A good example is the ballast water management plan. That's compulsory for any ship with a gross tonnage of 400 or more. So it's a key factor in determining what rules a ship has to follow.
Got it. So it's not just about fees, it's really about establishing a framework for safety and environmental protection based on the scale of the vessel.
Precisely.
That makes a lot of sense.
And then there's the economic perspective. Because it represents, the capacity of shipping, you can determine the total shipping capacity of a country or even a company by adding up the gross tonnage of all their ships.
Oh, wow.
And when a ship gets decommissioned, they take it off the registers and deduct its GT from the total. So it's this dynamic process, always adding and subtracting tonnage as ships come and go.
It paints a picture of a constantly evolving global fleet.
Uh,
Okay, so we've seen how we define a ship size, but let's get into the actual stuff that makes up these structures. What materials are we talking about when we say ship materials?
right. Well, if we just go back in time briefly, early ships were built primarily with mild steel.
Okay.
And the reason for that was its strength to weight ratio. It's strong, but it's not too heavy. And that was really important for building these big hulls.
Yeah, that makes sense.
Yeah.
So was it just one type of steel back then?
Well, not exactly. Even early on, they knew that different parts of a ship had different demands and needed to be stronger in different areas.
Makes sense.
But as classification societies, those organizations that set the standards for ships, as they evolved, they started specifying different grades of steel depending on their composition and what's called notch toughness, which is their ability to resist fracturing, especially in cold temperatures.
Okay, so notch toughness essentially means how well the steel can handle impacts or stresses without cracking or breaking, especially when it's cold.
Exactly.
That's got to be super important for ships, especially those operating in colder regions or rough seas. What are the different grades of steel they use?
Right. So typically you have 5 main grades: A, B, C, D, and E.
Okay.
And the grade they use for a specific part of the ship depends on how thick the steel plate is, what part of the ship it's being used for, and the amount of stress it's going to experience when the ship is at sea.
So I'm guessing the bottom of the ship, the part that's constantly in contact with the water, needs to be the strongest, right?
Absolutely.
It's taking the brunt of the forces from the waves, the currents, all that.
Right. You're thinking like a naval architect.
Well, I try.
So the bottom shell plating, the steel plates that make up the bottom of the hull, especially around the middle of the ship, that's what we call the midship zone, that area has the highest grade requirements
Okay.
because it experiences the most bending stress. You can imagine the hull flexing a bit as it moves through waves.
Right.
And the front part of the bottom, that needs a high grade too because it has to deal with the pounding from waves, especially in rough seas.
Makes sense. Now, what about the keel? That big structural beam that runs along the very bottom of the ship?
Yeah.
That's got to be pretty strong, right?
Yeah, absolutely. The keel plate is usually the thickest plate of all.
I would imagine so. Okay, so different grades for different areas depending on the stress they have to handle. Now, you also mentioned something called higher tensile steel, or HTS, in the outline. What's the deal with that?
Higher tensile steel, or HTS, is basically a stronger version of regular mild steel.
Okay.
And it's usually indicated by adding an H after the grade. So you have AH, BH, DH, and EH.
Gotcha.
These steels are tougher, they can withstand more stress before they start to deform permanently.
So is it just about making the ship super strong?
Well, it's more about efficiency and carrying capacity. See, as ships got bigger over the years to carry more cargo, the structure needed to get stronger too.
Right.
And if they just used thicker and thicker mild steel, it would make the ship super heavy, even when it was empty.
And that's bad because a heavier ship means it can carry less cargo, right?
Exactly.
So HTS is a way to make the ship strong enough, but without adding too much extra weight.
Exactly. By using HTS, you can use thinner plates and sections while still meeting the strength requirements.
So it's a win-win. A stronger ship that can carry more. Are there any downsides or special things to keep in mind when working with HTS?
Yeah, absolutely. Because it's so strong, you have to be very careful with the design and construction. The section modulus, which is a measure of how well a beam resists bending, has to be carefully calculated to make sure it doesn't deflect too much under stress.
Okay.
And welding HTS is also trickier.
Okay.
You need to use special low hydrogen electrodes and sometimes preheat the steel before welding to avoid cracks.
Gotcha.
And if you ever have to do repairs, it's really important to use the exact same grade of steel and matching electrodes. Otherwise, the repair could be weaker than the original structure.
Yeah, you wouldn't want a weak spot in your hull, especially if you're in rough seas.
Exactly. And thankfully, we have the shell expansion plan that shows exactly what grade and thickness of steel was used for every single plate on the hull. So even years later, if there's damage, you know exactly what to replace it with.
Wow, they really think of everything.
Mm.
Now, you also mentioned this thing called carbon equivalent. What's that all about?
So carbon equivalent, or CE, it's basically a way to combine the effects of different elements in the steel, like carbon, manganese, silicon, all those things,
Right.
and how they affect how strong and weldable the steel is. For mild steel, the CE is usually between 0.15% and 0.23%. But for the high tensile steel, it's higher, between 0.36 and 0.40%. And that's what makes HTS so strong. But it's also why you have to be more careful with the welding.
Gotcha. So different steels for different needs.
Yeah.
Okay, what about Arctic D steel? Sounds pretty cold.
Yeah, that one's for those really frigid environments where regular steel would just become brittle and break.
Right.
So Arctic D steel, it's not only stronger than regular steel, but it can also withstand impacts at really low temperatures, like negative 55 degrees Celsius. They do a special test called the Turpy V notch impact test, where they basically hit a notched piece of steel with a pendulum and measure how much energy it absorbs. Arctic D steel has to absorb a lot of energy before it breaks, even when it's freezing.
That makes sense. You'd want a ship to be able to handle the impact of ice or just the general cold in those extreme environments.
Exactly.
All right, so we've talked a lot about steel, but I know they use other materials too. What about aluminum alloys? Don't they use those for some ships?
They do. Aluminum alloys have some really great advantages, especially for certain types of ships or certain parts of the ship.
Okay.
For example, aluminum is a lot lighter than steel, but it's still strong. It's got a good strength to weight ratio.
Right.
And that's really important for speed, especially for high-speed crafts.
Yeah, makes sense. A lighter ship can move faster and more efficiently. What else is good about aluminum?
Well, it doesn't corrode as easily as steel, especially in seawater.
That's a big one for ships. Less corrosion means less maintenance. Right.
Exactly. And because it's lighter, it can also lower the ship's center of gravity, which makes it more stable, less likely to tip over. And in passenger ships, it might even allow them to make the ship a bit narrower or add more rooms without compromising performance.
So lighter, stronger, more stable, less maintenance. Aluminum sounds pretty great. What are the downsides?
Well, the main problem with aluminum is that it has a much lower melting point than steel.
Okay.
So it's not as fire resistant, which is a major concern on a ship.
Oh, yeah.
You need a lot of insulation to protect it from fire, and that adds weight and complexity.
Right.
Plus, aluminum is generally more expensive than steel, which can make a big difference in the overall cost of building the ship.
That makes sense.
Yeah.
Okay, so steel and aluminum are the main players. What about like cast iron or other materials? Do they use those at all in modern ships?
You know, it's interesting. Because of environmental concerns, things like the energy it takes to melt and cast metal, they don't use cast steel as much anymore. In the past, they used it for things like stern frames, those big structures at the back of the ship that support the rudder, and A-brackets, which support the propeller shafts. But nowadays, they mostly fabricate those parts using mild steel plates and sections that are welded together.
It seems like environmental concerns are influencing all sorts of decisions in shipbuilding these days.
They really are.
Okay, you mentioned deoxidized steel earlier. What's the story there?
Yeah, so deoxidized steel is steel where they've removed some or all of the oxygen from the molten steel during the manufacturing process. You see, when you're making steel, there's a lot of oxygen dissolved in the liquid metal, but as it cools, the oxygen can cause problems.
What kind of problems?
Well, it can react with the iron and form iron oxide, which can make the steel brittle. It can also cause little bubbles, called blowholes, to form in the metal as it solidifies, which weakens it.
So deoxidized steel is a way to make sure the steel is nice and clean and strong.
Exactly, and they do this by adding what are called deoxidizing agents to the molten steel, things like aluminum, silicon, and manganese. And depending on how much deoxidizer they add, you get different types of steel: killed steel, semi-killed steel, and rimmed steel.
Killed steel.
Yeah, it sounds a bit dramatic.
Yeah.
But killed steel is basically fully deoxidized, meaning they've taken out almost all the oxygen. This gives you a really clean and homogeneous steel, but it can sometimes have a problem with shrinkage as it solidifies.
Okay, and semi-killed.
Semi-killed is partially deoxidized, so there's still a bit of oxygen left, and that actually helps to prevent the shrinkage problems you get with killed steel. They use semi-killed a lot for structural steel because it's a good balance of strength and workability.
Okay, and what about rim steel?
So rimmed steel is barely deoxidized at all. And what happens is, as it solidifies, a lot of gas bubbles form near the surface, which actually creates a really pure layer of iron on the outside. It gives it a nice surface finish, which is good for things like sheets and strips.
So each type of steel has its own specific purpose and properties depending on how they remove the oxygen.
Exactly. It's all about choosing the right material for the job.
That's pretty fascinating. Okay, so we've got our steel, we've got our aluminum, but to build a ship, you need a plan, right?
Oh, absolutely. Ship plans are like the blueprints.
Right.
They guide every stage of the process, from building it to sailing it to maintaining it. And there are several important ones that each have a specific job.
Okay, let's start with the most general one, the general arrangement plan.
Okay, yeah.
Yeah.
The GA plan gives you a bird's eye view of the whole layout.
Okay.
Everything from the bottom of the keel to the top of the mast, front to back. They have to make sure it meets all the rules and regulations set by the IMO, those international conventions we talked about, like SOLAS and MARPOL, and the classification societies. It's a fundamental part of the ship's technical specs.
So it's like the architect's plan for a building, but for a ship.
Yeah.
What kind of information is on there?
Well, you've got the basic stuff like the ship's dimensions, its length, breadth, depth, draft,
Okay.
the class it belongs to, the classification society that certified it,
Okay.
how much it weighs, how much cargo it can carry, its gross and net tonnage,
Got it.
how many crew members it needs, its IMO number, call sign, what country it's registered in.
Wow, so it's like an ID card for the ship.
Exactly. And then you have all the details about the spaces inside, the
Mhm.
cargo holds, the tanks, the engine room, the accommodations for the crew and passengers.
And all of that is shown visually on the plan.
Right. It's a big, complex drawing, but it gives you a really good overview of how the ship is arranged.
That's really cool.
Oh.
Okay, what about the shell expansion plan? That one sounds interesting.
Oh, the shell expansion plan is really important, especially for building and maintaining the hull. Imagine you took the curved surface of the hull and flattened it out.
Okay.
That's what the shell expansion plan is. It shows you the shape of every single steel plate that makes up the hull and how they all fit together.
So you can see every plate, every seam, every weld.
Exactly. And it also tells you the thickness and the grade of steel used for each plate.
Oh, wow.
You can see that the bottom plates are the thickest, especially along the keel and in the middle of the ship where the stress is highest. And the side plates get thinner as you go higher up, except for the topmost row, which needs to be stronger because of wave impacts.
That's incredibly detailed. Why is it so important to have this plan?
Well, for one thing, you need it to calculate how much steel you need to build the hull in the first place, how many plates of each size and thickness.
Makes sense.
But it's also crucial for inspections and repairs later on. Every 5 years, a ship has to go into dry dock for a thorough inspection.
Right.
And the inspectors will use the shell expansion plan to check for any corrosion or damage to the hull plates. And if they find any problems, they can see from the plan exactly what kind of steel was used originally, so they can replace it with the right material.
So it's like a maintenance manual for the hull.
Exactly. It ensures that the ship stays strong and safe throughout its life.
That's really impressive. Okay, what about the capacity plan? What's that one for?
The capacity plan is all about the liquids. It tells you how much of each liquid the ship can carry.
Liquids, like what kind of liquids?
Everything. Fuel, obviously.
Right.
Lube oil for the engines, fresh water for drinking and washing, ballast water for stability, bilge water, which is the dirty water that collects in the bottom of the ship, even sewage. If it's a tanker, it'll also show the capacities of the cargo tanks.
So it's like a giant inventory for all of the liquids on board.
Exactly. And it's not just about how much they can carry, it also shows where each tank is located, its dimensions, and how much it weighs when it's full.
And why is all that information important?
Well, for one thing, it's crucial for stability calculations.
Oh, right. We talked about ballast water earlier.
Right. So the capacity plan helps them figure out how to distribute the weight of the liquids to keep the ship balanced and stable. It also helps them calculate something called free surface effect, which is how the movement of liquids in partially filled tanks can affect the ship's stability.
Okay.
Plus, it's important for operational planning, knowing how much fuel you have, how much fresh water. All those things are essential for running a ship.
That makes a lot of sense. Now, what about safety? I'm guessing there's a plan for that too.
Absolutely. The Fire Control Plan, or FCP, is all about fire safety.
Okay.
Every ship over a certain size has to have one, and it shows the location of all the firefighting equipment on board.
So it's like a fire safety map for the whole ship.
Exactly. It shows you where all the fire pumps are, the fire hoses, the extinguishers, the sprinkler systems.
Okay.
It also shows the fire-resistant divisions within the ship, the bulkheads and doors that are designed to stop the spread of fire, and it even shows the escape routes.
Wow.
It's a very detailed and essential document for ensuring the safety of everyone on board.
And I'm guessing this plan needs to be really clear and easy to understand in case there's an actual fire.
Oh, absolutely. It needs to be readily available and prominently displayed so that anyone can quickly find the information they need in an emergency.
Makes sense. Okay, so we have a plan for fires, but what about when a ship needs to go into dry dock for maintenance? Is there a plan for that too?
Yes, there is. It's called, appropriately enough, the dry docking plan.
Okay.
It's basically a guide for how the ship should be positioned and supported in the dry dock. It shows the arrangement of the keel blocks, which are the big supports that hold the ship up, and it also shows the locations of any sensitive underwater equipment, like the sonar dome or the speed log, so they don't accidentally damage them when they're putting the ship down on the blocks.
So it's like a set of instructions for the dry dock workers.
Exactly. It helps them prepare the dry dock properly and ensures that the ship is lifted out of the water safely and without any damage.
That's really important. What about life-saving equipment? Yeah. There has to be a plan for that too, right?
You bet. The Life-Saving Appliances Plan, or LSA plan, shows the location and details of all the lifeboats, life rafts, life jackets, everything.
Okay.
And it's not just a list. It also shows how they're supposed to be launched and used, how to lower the lifeboats, where the muster stations are, all that.
So it's a guide for both the equipment and the procedures in case of an emergency.
Precisely. It's another crucial document for ensuring the safety of everyone on board.
All right. And finally, there's the lights, shapes and sound signals plan.
Right. The LSSS plan is all about how the ship communicates with other ships, especially at night or in bad visibility.
Okay.
It shows the type and position of all the navigation lights, the shapes they have to display during the day, and the sound signals they have to use. Like the foghorn or the ship's whistle.
So it's basically a visual and audible language that all ships understand.
Exactly. And it's based on international regulations, the call regs, so everyone follows the same rules, which is obviously very important for preventing collisions.
It's amazing how many different plans are required to build and operate a ship safely. All right, now let's talk about how these massive things actually move and turn in the water. What's the secret to steering a ship?
Well, the rudder, of course, is the key.
Right, but how does a rudder actually work? I mean, it seems like such a simple thing, just a big flat plate underwater, but it controls the direction of this massive vessel.
Yeah, it is pretty amazing when you think about it. So basically, when you turn the rudder, it creates what's called hydrodynamic force.
Okay.
Imagine water flowing smoothly around the hull of the ship. When you stick the rudder out at an angle, it disrupts that flow.
Okay, so it acts like a kind of a wedge in the water.
Exactly. And that creates a difference in pressure on either side of the rudder. Higher pressure on one side, lower pressure on the other, and that pushes the rudder and therefore the stern of the ship in the opposite direction.
So it's like pushing against a wall of water. Does the shape of the rudder matter?
Oh, absolutely. The shape of the rudder is crucial. It's designed like an airfoil, similar to the wing of an airplane.
Really? I never would have guessed that.
Yeah, it's all about generating lift, just like a wing. But in this case, the lift is sideways, pushing the stern of the ship to turn it.
Fascinating.
Yeah.
And I'm assuming this force acting on the rudder must be pretty significant, especially on a large ship moving at speed.
Oh, yeah. It can be huge. And all that force is transferred through the rudder stock, which is the shaft that connects the rudder to the steering gear up in the ship.
So designing that rudder stock must be a pretty critical part of the whole process.
Oh, absolutely. It has to be strong enough to withstand those immense forces, especially in rough seas. Otherwise, it could snap.
And that wouldn't be good.
No, it wouldn't.
Not at all. Now, I've heard the term balanced rudder. What makes a rudder balanced?
A balanced rudder is designed so that a portion of its area is actually in front of the axis of rotation, the point where the rudder turns.
Okay.
And that forward part helps to counteract the force on the main part of the rudder, so it takes less effort to turn.
So it's like a self-centering rudder in a way.
Yeah, kind of. It's not perfectly balanced, but it makes steering much easier, especially at high speeds.
That makes a lot of sense.
Yeah,
So is there a limit to how far you can turn a rudder?
there is. If you turn it too far, something called stalling happens.
Stalling like an airplane.